This is me, after 8 hours of work. 8 hours of making this. Whatever this is. What the heck is this? This substance is not what we asked for. This is bleach. Why did we make this again? Good God. Today we'll be looking at how we got to this point. Where we're pouring bleach into a bottle. It all started here, with this. What the heck? Why are we making gelatin? This is a science video. Gelatin is a good membrane material. I've seen it used as a membrane before in the day. We're gonna go ahead and make it into a membrane. Now basically when you do electrolysis, there's ions in the liquid, which have disassociated from their original compound, basically dissolving. What happens when we do electrolysis is that we basically pull the different ions, the cations and anions, to the cathode and anode respectively. However, when you have both the anode and cathode in the same solution, then very interesting things happen where these anions and cations come together and form a new compound, and do some whack stuff. To stop this from happening, we need to separate these things. Now there's many ways of doing this that exist. One way is to separate them using a layer of mercury at the bottom, and then just have two separate cells with the mercury connecting them. This method was used industrially for a very long time, but has been phased out by selective ion membranes, which don't allow certain ions to pass through, but they do allow the sodium ion. Basically, this gelatin is going to act as a membrane. The gelatin will act as a membrane which is not selective. However, it should be sufficient for separating our anode and cathode reactions and preventing their products from reacting. Now, I'd prepared quite a few of these just in case they were not to my satisfaction. But when they cured the next day, it was time to go. We started at 9. And I opted to use a vice grip to hold the setup. This is mainly due to the fact that I have no other way of clamping it. The first component I decided to fix into the vise was the membrane. This tube was, well, the most perfectly sealed one as far as the membranes go, because I had 3 of them. And 2 of them were, well, one was iffy and the other one was definitely not sealed at all. And then I brought out the electrodes, which we have the graphite and the copper one. Now the reason I chose copper is because I have a bit of copper wire, and I can easily just make it as big as I want, as large as I want, make it in whatever shape I want. It's nice, as opposed to things like a nail or something. So the first side of this partitioned cell is going to run salt water. This side is going to be the anode. We're going to run a positive charge into this guy, and he's going to have graphite because it will be able to resist the chlorine. Now, it was very important that I make sure that everything is sealed, because if anything was leaking, it would be the end of the world. Literally. So I made sure to get that thing nice and fixed in there, nice and snug. And then it was time for the red side, or the cathode. Oh wait, did I get those backwards actually? No wait, never mind. The only reason there's hydroxide that's going to form at the cathode is because we're basically electrolyzing just regular water on this side. So that means that the hydroxide can form over here. There's probably some hydroxide on the other side too, honestly. But basically the cathode being on this side and the hydroxide forming on this side will make sodium hydroxide. Which is why it's very bad if this were to leak, because that could basically just melt your hand off. Well, that's an exaggeration, but it is very not fun. And to be honest, copper does actually destroy hypochlorites that might form if chlorine decides it wants to go to this side. I don't know why chlorine would, because it's supposed to go to the anode. Although hydroxide forming on this side could be electrostatically pulled over to the other side. But the other side might also form some, so hopefully that happens. Now honestly, I was quite surprised when this thing didn't leak at all, because before I tested this and it leaked. Well, thankfully, this duct tape plus electrical tape solves all problems. And like I said before, if it leaks it would be very bad. Now it's time to add the salt water. Now this is oversaturated, there's undissolved salts. The reason for this is that as the salt is electrolyzed, we will be able to dissolve more. Of course, we need to make sure the exact amount is filled in there, because if it's too full, then the alligator clip becomes an electrode, which is not what we want. We want the graphite to be an electrode. And I was a little concerned this first time that we had accidentally overfilled it, which resulted in me pouring it back out. And then we have to load the side with water. This side is the cathode. It's going to pull sodium across the membrane. Now water is very covalent, so it doesn't really like to electrolyze on its own. Now basically, when we add a current to this, Some kind of magical electrostatic force allows us to pull stuff across the membrane. And since the cathode is negatively charged, it will pull the positively charged sodium across. This is honestly some strange sorcery. I don't like electricity. However, when the sodium ions finally arrive on this side, the water will just give up and stop being so covalent, and will actually do what we want it to do, which is electrolyze, of course. Now this is going to come in handy, this valve at the bottom. This allows us to dump the sodium hydroxide solution that forms on this side. This is more handy than I ever could have thought it would have been. I honestly only thought we would use it for that, whenever this side becomes too saturated with NaOH. But you'll see it in action later, quite a few times. I was really thankful that last time I labeled which one is where I need to plug the stuff in. I honestly should have labeled which side needs to be the cathode and anode sooner. I should have done that. At 10:44 a.m., all of the setup had been completed, and we had finally plugged everything in, even the electricity. Over the course of the first few hours, absolutely nothing happened. In fact, there was no gases forming, which the goal of this project was to collect some gases. And around 1:23 or so, I had finally decided that we need to try some things. I decided to try seeding some sodium ions into the cathode tube using sodium bicarbonate, which resulted in absolutely nothing happening. The reason I chose sodium bicarbonate is because it doesn't contain chlorine. This is very essential because we don't want any of those chlorites, hypochlorites, or hypochlorates, any of them forming. We don't want none of that. And then I made the greatest choice ever, to increase the voltage. Now with this there comes some dangers because high voltages can destroy electrodes. Usually to increase the current density you just increase the amperage, but here we're increasing the voltage, which is, and also amperage probably too. The voltage increase resulted in something happening. I noticed some kind of bubbles in there. And with this I decided that I don't want the sodium bicarbonate in there. I'm gonna just dump it all. Like I said, this came real in handy. A feature I intended for something else was able to be used for, well, another purpose. After refilling the cathode tube, now eventually those particulates that I noticed in there, probably this was around 3 p.m. or so, there was a lot more of them. A lot of them. And I don't know if these were bubbles or what they were. I don't think they were bubbles. But they might have been, and it might have actually worked. Because every time I tested with the UV light, some kind of current was passing through it because the light would light. Since we're dealing with some potential sodium hydroxide, we may as well test if it reacts with aluminum. Throughout this experiment, I did this quite a few times, and even at the end, once I'd collected quite a bit of this solution, none of it reacted. I then found more 9-volt batteries, and I decided, you know what's better than one 9-volt battery? Well, why not 27-volt battery? Oh my gosh, why are these all in parallel? Why are these all in series? More voltage equals more fun. But I also knew this would probably melt the electrodes. I didn't really care at all. This electrode has survived much worse. It's been snapped in half. It's been through it. And then I always go over to here and check using my eyes to see if there's any hydrogen gas bubbles forming on this side. Which there was, in very small quantities. It's not like any of the other experiments where it's going very rapid. And then the bubbles stopped forming on that side. And I decided, it's dump time. If this side were to become saturated in sodium hydroxide, then in theory it should stop producing bubbles. Of course, it may still continue producing bubbles and continue to be electrolytes. I don't have any sodium hydroxide to test with. I probably should get some. A couple hours pass and I look inside the anode tube. I had done this one time before and I regretted doing it because it smelled very much like chlorine. I did not like that at all. But this time I looked in and I saw that the anode looked like it had melted. This would have meant that I had to shut everything down. So I had to take everything apart and diagnose the problem. First I had to dump out the cathode tube, and then the anode tube. And to my surprise, rather than a black viscous sludge, we received the welcoming smell of chlorine, and a very yellow liquid containing some iron oxide, presumably from the alligator clip. One part I was most curious about was if the gelatin had survived. It in fact survived way better than I expected. I thought it would at least be yellow on this side because of chlorine or something, but unsurprisingly, this side also had more of the hypochlorite solution and also some salt. Now, for general purposes, we're just gonna call this bleach instead of hypochlorite or hypochlorite. I have no clue which of those it is right now, and I know they're two different things. And unsurprisingly, since we poured out a bunch of orange stuff, the anode had survived, and will serve again in the future. Honestly, this has been with us since the beginning. I can't believe it survived this long. The cathode had turned gray at some places, which was quite interesting. Although you can't really notice it on the camera since it's such a thin cathode. And lastly, it was time to filtrate. The reason we're filtrating this is because I fear it has some of the wonderful electrolyte in it, but also the wonderful oxides from the metal. Filtering removes those. You could also distill it, but that would be kinda, I can't do that. Also, what do you get when you distill bleach? Because it's just, bleach isn't water, right? It's just dissolved in water, right? You get some funny powder? Well, actually, bleaching powders are a real thing, but I'm not too sure if you can have solid hypochlorite, or just solid bleach in this case. And that is how we got to now, where we're filling a bottle with bleach and now labeling it. This is the most concentrated I have ever made this stuff at. I think in the first run where we made this, way back in the day, when we made iron oxide Mars dust, I think it was clear, and now we have this yellow stuff, which is similar in appearance to what you can expect from a store-bought stuff. Slightly less viscous though. Now this video took an entire day to make, and I am right now overtime. But that's perfectly fine, and I enjoyed making it. I would like to thank you all for watching. If you would like to become a channel member, then please do so. But for now, I'm gonna go to bed.